Hey y'all. Welcome back to, or maybe first time to, in case you missed it, loved it, hated it so much you want to watch again. Um, this is week 4, session 8. So, tying off integrals and work. Sorry, just as a preface, this session is super think pair share focused. And so if you are not here and you feel as though you need more support or you want to work through things with someone, please reach out to us. It can be difficult to approach problems on your own sometimes, and we want to acknowledge that. And these problems are pretty challenging and meant to kind of confuse you a little bit. So let's start with a quick review of work. So work by a force is done on an object when this force vector has a component in the direction of the object's motion. When the force is not constant, we can utilize an integral to find the area under the curve. So we're diving right into a problem. So I'll read this out, pause it, take some time to try and solve it. In session, I think we would do 5 minutes alone, then 10 minutes in pairs. So, 1 kilogram bucket filled with 5 kilograms of water is lifted up a 20-meter well at a constant speed. As it's raised, water splashes out of the bucket at a rate of 0.1 kilograms for every meter it moves up. So, draw a free body diagram for the rope bucket system. Sketch a force versus displacement graph for the tension between the rope and bucket. And then using an integral, determine the work done by the rope through the scenario. So pause the video, take a try. An additional question that we have on here that if you want to try and answer, does it make more sense to not fill it all the way initially? Why not? Pause, think about it for a minute. All right, let's dive into the solution then. If you didn't try this out, I would recommend trying it out, but either way, here we go. So draw a free body diagram for the rope/bucket system. This middle box is just the prompt so you remember, and the diagram on the right. So our free body diagram is only going to have 2 forces. On the bucket, we're going to have the force of gravity, which is equal to mg, and the force of the tension, which is equal to negative force of gravity. We know that because we know that it's sort of counteracting it. We can solve for the force of tension equal to the negative force of gravity. So the force of gravity is mg, which is 5 kilograms minus 0.1 kilograms times x, some x, times negative 10 meters per second squared. And so we can, if force of tension is a negative, we just sort of multiply all that by -1. So basically what this is saying is mg, and so we're doing 10 for g here, and then m is changing, so it's displacement dependent, so we have an x in there. Looking at the solution plot here, because the bucket is rising at a constant speed, we know the bucket is not going to be accelerating, meaning that there will be no net force. With no net force and the water splashing out of the bucket, that means that the force acting on the bucket is changing with how far the bucket has moved up and how much mass it has lost. We already solved for this tension equation, which essentially is just the mass with how much it's changing based on the displacement times the acceleration due to gravity. And so looking at this plot, we just plug in sort of at the beginning. We know that x is going to be 0, and so we have the full 5 kilograms in there. And then at the final tension, we know that it's gone 20 meters. And so we know it's going to be 5 minus 0.1 times 20. So we basically go from 50 newtons of tension to 30 newtons of tension just based on the loss of mass over the system. Finally, using an integral, determine the work done by the rope throughout the scenario. So the force equation equals the force of tension. And so we know work is going to be force with the dot product of distance, which is, reminder, a form of multiplication that only uses the force components in the direction of the motion. And that's equal to the integral from the initial position to the final position of that force equation with respect to that position. So plugging in everything we know that our initial position is 0 meters and our final position is 20 meters. We also know our force equation is going to be that initial mass minus the change in mass based on the displacement times g. When we take that integral, when we solve that a little bit more, we can see that it's going to be 50 newtons minus 1 newton meter times the displacement. So basically what we did is we just multiplied that g into the equation just to get a bit of a simpler thing to look at. So when we take that integral, 50 newtons is just going to have an x tacked onto it, and then that 1 newton meter times x, we know that the power rule is going to tell us that x is going to be squared now, and everything's divided by 2. So it's minus a half Newton meter times the displacement squared. So we can solve that by plugging in 20 and 0. We know that when we plug in 0, because both are being multiplied by it, your resulting work from that initial point is 0. So we just need to solve it with 20 meters plugged in for x. So we can do 50 newtons times 20 meters minus 1/2 Newton meter times 20 meters squared. What we get at the end of that is 800 joules. Again, if you have any questions, please reach out. All right, let's introduce energy just a bit and its connection to work. We're going to dive more into this next week. So energy is the capacity for doing work. Energy can neither be created nor destroyed, but transformed from one kind to another. All forms of energy are either kinetic, energy in motion, or potential, energy stored in an object. The net work done on an object is equal to its change in kinetic energy. There are some equations in the top right here. So potential energy, PE, is equal to mass times gravitational acceleration times height relative to the origin. And then our kinetic energy is going to equal 1/2 mass times velocity squared. Just a breakdown of the energy, the units of energy is the same as the units of work. So it's joules, it's Newton times meters, or kilograms times meters squared over seconds squared. With that being said, let's dive into the next think, pair, share, or for you all, think, maybe be confused, reach out, and then we'll go over the solution. The ball is thrown straight up here, so at t equals 0, a 1 kilogram ball is thrown vertically upwards at a speed of 4 meters per second. We want you to graph the energy versus time plot, drawing separate curves for the kinetic and potential energies. At the ball's peak, what is the potential energy? And then what is the net work done to the ball between t equals 0 and just before it's caught? So again, pause the video, take some time, try and solve that. And then we have an additional question, and then we'll go over solution. So our additional question, if you have time and you want to think about it, what would happen if we changed our origin and coordinate frame in this problem? Think about how that can impact the determination of the potential energy. All right, and then let's dive into the solution. So our equations that we gave you are in the top right in this blue box, but let's just dive right in. We want to start by graphing the energy versus time, drawing separate curves for kinetic and potential energy. By solving for the initial kinetic energy and potential energy, we're able to find that the total energy in the system. And so the initial kinetic energy is going to be 1/2 times the mass, 1 kilogram, times the initial velocity squared, so 4 meters per second squared. And that equals 8 joules. Our initial potential energy with the origin we defined is 0. We know that because the height is going to be 0. Just a shout out, we're plotting in terms of time. Just to be explicit about that connection, the height is changing in terms of time and the velocity is changing in terms of time. And so that's how those connect to our potential energy and kinetic energy equations. We can see that the total energy is going to add up to 8 joules. So in this situation, it's only kinetic energy at the beginning. And then we plotted that out because we know the total energy is sort of staying the same in this system. So we can find the time at the top because we know the velocity at the top is 0 meters per second. And so we know that it's going to be 4 meters per second minus the gravitational acceleration times a given time is going to give us 0. And so we've solved for that time to be 4/10 of a second. We know that the kinetic energy, we're going to slow down. We have a steady negative acceleration. If we're thinking about working backwards to velocity, we know that that's going to look like a curve. So we're slowing down quickly, and then slower and slower, we reach 0, and then we go back and we're getting faster and faster, but in the negative direction. And so what this means for the potential energy is we know that the ball, this is quite literally the path of the ball, right? Like it starts at 0 and then it goes up and then it reaches the top and then comes back down. We know that the time it takes, sort of because of the acceleration, we know it's going to move a bit quicker at the beginning and at the end. So at the ball's peak, what is the potential energy? We know here that the potential energy at the top can be found by the calculation of the kinetic energy at the beginning. We know the energy remains constant, and at the top, the kinetic energy is 0 because the ball has 0 velocity. And so then we can understand that the potential energy at the peak has to match the initial kinetic energy, which is 8 joules. We can also check that understanding by thinking of it, that's where the ball is the highest point, and so it makes sense for that to be the peak of the potential energy as well. Finally, what is the net work done by the ball between t0 and just before it's caught? So these yellow highlights are sort of our limits. So the net work done on an object is equal to its change in kinetic energy. So the sum of the work is the final kinetic energy minus the initial kinetic energy. When we solve that, we can sort of simplify this equation and this problem quite a bit just by the conceptual aspects, which is something that you'll get a lot of practice with at Olin. Oftentimes, the problem can be simplified if we think about it conceptually first, and so you don't have to do a ton of math of taking integral of all of this this work equation. So we know the final and initial kinetic energy are actually the same, and so we can understand that the net work is actually going to be 0 joules. So we want to revisit the bucket with you all. So we want to take a few minutes to ask the question of thinking about the potential energy and kinetic energy in the system. Are they changing? Why? Why not? And then also think about the total energy of the system. Does it stay constant like the ball did? And why not? Let's take a few minutes and then I'll maybe just go over it a little bit. So we know that there's going to be a change in the kinetic energy. The total energy is not going to be constant because we're losing energy because we're losing mass. The only reason that the kinetic energy is changing because of, even though it's going at a constant velocity, is because of that change in mass as well. So that because we're losing mass, we not only don't have a constant kinetic energy, we're also losing energy in the system. So this is based out of the fact that this is an open system rather than a closed system. So far, we've been working in closed systems, and so we've been making a lot of assumptions. We just want to point out that open systems do exist. They can be useful. They're also super confusing sometimes. And so just to sort of start thinking about the assumptions we're making when we're looking at problems. All right, we will end off this session with a reflection. I welcome you to try this on your own. No pressure, of course. So take a moment to reflect on the following prompts before we come together to discuss. Obviously, we're not going to be able to discuss if you're watching remote. But what did you feel during this session? What connections did you see between this session and your educational experiences? I would welcome you to reflect on it. You can pause. I'll share a quick story of my own, which you're welcome to listen to before, after, or not at all. Back in high school, so with these problems were a lot of work, and maybe doing them asynchronously allowed you to have more time, but in session, we suspect that some people would not be able to finish them in the given time because it's just a lot of work. Sometimes that can be difficult, and we want it to acknowledge that. I've felt that way before at Olin. I felt that way before, long before Olin. In my first AP Physics class, I failed the first test I got, and I was so devastated. But I think that I have grown a lot from that experience, and that whole course allowed me to learn that failing is okay, and it's an opportunity, and to use it that way rather than using it as a way to get down on myself. And so we're hopeful that when you see challenging problems, you'll see it as an opportunity, and you'll be able to reach out if you need help, and you'll also be able to acknowledge that it's okay to fail. I think that that's something that everyone is always working on. And so thank you for engaging with this reflection, if you did and if you can. Otherwise, that is it for this session 8. And thank you for watching the video. Thank you for engaging with us. And we hope to see you next session.